Hi everyone, welcome back to another Calculus 12 lesson. Today we are looking at Chapter 2, so we're going to do 2.1, which is working with derivatives. And we're going to transition from limits into derivatives and look at the connection and what they have to do with one another. So the first example says find the slope of the tangent of x squared at value x equals 3. So this is sort of a nice way to transition in because we're just reviewing something that we have already learned how to do before. So just to remind you and build in that little bit of review, we're looking for the limit as h approaches 0 of f of 3 plus h minus f of 3 because 3 is our point of interest here, and that's going to be over a value of h. So again, we're looking for the tangent at this value x equals 3. That's the reason why I have this 3 here, so you can see where it's coming from. And then we're going to take our function x squared and use that for filling it in here. So we have the limit as h approaches 0. And here, what I'm going to do is I'm going to take this x squared, and if I want to figure out f of 3 plus h, that's going to mean instead of x squared, it's going to be 3 plus h squared. So you can see where that's coming from. And for the other part, if we have minus f of 3, I'm going to take that x squared and I'm going to do minus 3 squared. So you can clearly see where that's coming from. And the whole thing is still going to be over this value of h. So again, we've been doing this actually for quite a few lessons and working our way through this. So I am going to skip some steps. Just a reminder, this means 3 plus h times 3 plus h, and we would FOIL out and distribute all those values. And after doing all that work, we would get 9 plus 6h plus h squared minus 9, and the whole thing would be over this value of h. And to make this super clear, this 3 plus h squared is where I'm getting all of this from, and this minus 3 squared is where I'm getting this from. So after we work our way through all of this, simplify things, we can see that those are going to cancel. There's an h at the bottom. I could factor out the h up here. I would be left with the limit as h approaches 0 of 6 plus h, and when I plug in 0, so maybe I'll write that out, the limit as h approaches 0 of 6 plus h. Well, if we're looking for h approaches 0 and I plug in 0 there, I'm just left with this answer or value of 6 after doing all that work. Okay, so we're doing this so I can make a comparison to finding the slope function of f of x equals x squared. So I want to show you the comparison. If we're now looking for the slope function, it's different than what I was asking for on the left side here. So let's take a look at how that shows up. We're still going to do this. The limit as h approaches 0 of x plus h squared minus x squared. So I'm not filling in the 3 or any of the values that were given on the left. We're just looking for this generally when h is approaching 0. So in order to do that, I would still work my way through the same type of work in algebra to get there. I would take this x plus h and I would distribute it. I'd do x plus h times x plus h, and I would get x squared plus hx plus h squared, and then at the end I'd have minus x squared all over h. So notice I'm doing the same things as on the left-hand side. I just didn't fill in that x equals 3 value. I just left it as x. And the reason is because here it asked for the slope function. So I'm looking for like a general equation for this. So x squared minus x squared is actually gone. Notice how there's a h at the bottom, there's a h in there, and there's h squared, so I can get rid of that. And so when I simplify this, the limit as h approaches 0, when I look at this, I'm left with 2 from right here. 2x actually. We got rid of the h, and then here I still have a plus h at the end. But notice, if I'm looking for h approaches 0, when I plug in 0 into here, it's actually gone. So after doing all of that, I would get that this is just equal to our function or our value of 2x. And I'm going to show you this new notation that looks something like this, f prime of 3. So at this point I could plug in 3, would be, sorry, let me go back a little bit. I'm trying to skip a step here, but I want to write it down. So my f prime of x is this function 2x. So I'm going to define this for what we're doing today. This is called our slope function. That's the general equation for the slope function. So I wouldn't have to find it specifically for 3. I could use this for any point on that graph to find the slope. But in this particular case, we were looking for 3. So I'm going to do f prime of 3. That's the notation we would use, would be 2 times 3. So I still get that same value of 6 that I got here. So we get to see that they are exactly the same and it means the same thing. Okay, so taking a look at this, derivative functions and notation. So that you can understand the concept, I've drawn 2 of these graphs side by side so we can sort of compare and contrast them. The one on the left here, this is the initial parent function. And the one on the right represents what the slope of the slope function would look like, what the graph of the slope function would look like. So I used the same one that we were just working with because it's fresh in your memory. So this f prime of x, this is our slope function. And so what this is saying is, like, if I wanted to know the value at, let's say, 3, the one we just did, this would allow me to figure out what the slope is at that point. It would be 3 times 2, so it must be up here at a y value of 6. And then if I wanted to figure out like what it's at 4 or 5 or anywhere, this equation, this slope function equation, f prime of x, allows me to figure out the slope at any different point. So I wanted to just show you the graph so you could get a visual picture of what this looks like, but we'll actually move into how to calculate this stuff. So that I can sort of tie these in together with something that you already know, let's take a look at this new notation. So this stuff in green, f prime of x, maybe I'll do this in green as well, f prime of x is the same thing as the limit as h approaches 0 of f of x plus h minus f of x over h, so the stuff we've been working with the last few days. And with the green arrow here, I'm showing you that this is the derivative of f of x, and we would call it f prime of x. I guess I didn't need that up there. Let's get rid of it because I've put it at the bottom. In pink here, this process, when generalized, is called taking the derivative or differentiation. So these are new terms for you. So taking the derivative and differentiation. This is new vocabulary that you're also going to need to know moving forward. Okay, also, today's the first day I'm introducing you to this, but you'll see it's going to come up time and time again in different forms. So this is the one in green that we had just finished talking about, f prime of x, just like the one I showed you. That's the same thing as saying d dx of f of x, or dy dx, or y prime. They all mean the same thing. They're just different ways of, like, they're different notations that actually mean the same thing. I think the one we'll use most frequently is probably this f prime of x and y prime. They just seem to be the ones that are easiest to work with. But know that the other ones are also, they mean exactly the same thing. And I think as we work with this and you feel more comfortable, you will become more familiar with them. Okay, so then the only other thing to look at before we finish this off is that some functions are non-differentiable, or we can't take the derivative of them. That happens when we have vertical asymptotes. So this is again looking at stuff we've done before. The slopes race towards positive infinity, so moving in this direction here when we look at positive infinity, or they're moving to negative infinity, which was headed in this direction here. So therefore, if the slopes are headed in different directions, f prime of 0 is undefined, and the limit does not exist because they're not approaching the same value from both sides, which is the definition of a limit. Okay, so also we can't take the derivative, or it's non-differentiable, when we have jump discontinuities. So we've seen graphs like this before. If we have this function absolute value x over x, and we have a big gap like this, kind of for the similar reasons to what we just looked at, we can see by definition of limit, we would want the values to approach the same value from left and right, and clearly they don't here. So f prime of 0 again would be undefined, and the limit does not exist. And the last one is when we have kinks. So this happens when we have absolute value functions. And so the reason for that is f prime of 0 is also undefined. If we tried to take the derivative at this point, well, you can't. It's going in all these different directions. So it's undefined and the limit does not exist. At any peak or point, there are infinite tangent slopes. So therefore, the slope is undefined. And that's the reason we can't take the derivative at that point. So there's your work for today for 2.1, and I hope that you found this useful.